All right, welcome. Today, we're going to dive into a classic physics problem that, I promise you, looks way harder than it actually is. By the time we're done here, you'll see how just a couple of core ideas can cut right through all the complicated language. So, let's get into it.
So, where does our challenge come from? Right here, i.e. Irodov's Problems in General Physics. Now, if you've been in a physics program, you've definitely heard of this book. It is legendary for its tough but really insightful problems that seriously build up your physics intuition. And today, we're going to take one of them down.
You know, the first rule of solving any physics problem is pretty simple. Just stop for a second, take a breath, and figure out what is really being asked. So let's lay this whole thing out.
Okay, there it is, the problem in all its glory. Just take a second to read it. Now, I know what you're probably thinking. Words like centrifugal force of inertia sound kind of weird, right? In that part about an arbitrary path, that might feel impossible. Like, how can we solve it if we don't know the path? But here's the secret. Don't worry, those phrases aren't roadblocks. They are actually the keys that are going to unlock the whole solution for us.
So before we start plugging in numbers, we have to get a really good handle on the two big physics ideas that are going on here. First is the concept of work, and second is this thing called a fictitious force.
So in physics, work isn't about how much you sweat. It's all about energy transfer. It's what happens when a force pushes or pulls on an object and makes it move over a distance. That formula, W equals the integral of F dot dr, yeah, it can look a little scary, but the idea behind it is super simple. You're just adding up all the tiny little pushes and pulls from the force as the object moves from its starting point to its final destination. That's it.
And that brings us right to the heart of this whole problem. What in the world is this centrifugal force? You've definitely felt it, right? On a merry-go-round or when a car takes a sharp turn, it's that feeling of being pushed to the outside. But is it a real force, like gravity? Well, the answer's a little more interesting than that.
Centrifugal force is what we call a fictitious or inertial force. Now, don't let the word fictitious throw you off. It's an apparent force that seems to exist when you're looking at things from inside a rotating system, like when you're the one on the merry-go-round. It's not a real interaction between two objects. It's just a consequence of your own inertia in a spinning frame of reference.
Okay, this right here is what makes it all make sense. Imagine you're standing on the ground watching your friend on a merry-go-round. That's the inertial or stationary frame. From your point of view, you see the merry-go-round pushing inward on your friend, forcing them to go in a circle. But for your friend on the ride, in that non-inertial rotating frame, it feels like some mysterious force is trying to fling them outward. That feeling of being pushed out, that's the centrifugal force.
And now we come to the part of the problem statement that probably confuses everyone the most. But guess what? It's actually the secret that makes this problem super simple. I'm talking about that arbitrary path.
Seriously, whenever you see a phrase like this in a physics problem, a little light bulb should go on in your head. It is a massive hint. The problem is basically screaming at you that the specific zigzaggy path the object takes to get from point 1 to point 2 doesn't matter one bit. And there's a really good reason for that.
So let's break down exactly why the path doesn't matter. First, the centripetal force is what we call a central force. It always points straight out from the center, right along the radius. Second, its strength, you see it in the formula, m omega squared r, it only depends on r, the distance from the center. And because both its direction and its strength are tied only to its radial position, the total work it does only depends on the change in radius, where it started and where it ended. The specific journey it took in between, totally relevant.
And here's the perfect analogy for this. Think about climbing a mountain. The work that gravity does on you only depends on your starting altitude and your ending altitude. It makes no difference if you took a long, winding path with switchbacks or if you just scrambled straight up the side of a cliff. All that matters is the net change in your height. Our centrifugal force problem works the exact same way.
All right, we've done the heavy lifting. The conceptual part is over. Now that we actually understand the physics, the math is, believe it or not, surprisingly easy. Let's get to the calculation and see how this all comes together.
So, we start with our main definition of work. Then, we just substitute in our specific formula for the centrifugal force, which is F equals m omega squared r. And that gives us a pretty simple integral to solve. The work is just the integral of m omega squared r with respect to r from our starting radius r1 all the way to our ending radius r2.
Okay, here are all the numbers the problem gave us. Mass is 0.10 kilograms, angular velocity is 5.0 radians per second, initial radius is 30 centimeters, final is 50. And right here, this is the first classic trap for students. You have to convert your units. We need everything in standard SI units, so R1 becomes 0.30 meters and R2 becomes 0.50 meters. Don't forget this step.
Now we just follow the recipe. First, we set up our integral with all our known values. Now, since mass and omega are just constants, we can pull them right outside the integral. The integral of r with respect to r is a basic one. It's just 1/2 r squared. So our whole expression for work simplifies to 1/2 m omega squared times the final radius squared minus the initial radius squared. From there, it's just plugging in the numbers and doing the arithmetic.
And boom! There you have it. The work done by the centrifugal force of inertia is 0.20 joules. See? That wasn't so bad after all.
So we got the answer, and that's great. But the number itself isn't the most important part. What did we actually learn about physics by going through this whole process? Well, first, we learned that even though they're called fictitious, these inertial forces can absolutely do real work inside their own frame of reference. Second, we've basically proven that arbitrary path is code for path independence, which tells us to ignore the journey and focus only on the start and end points. And finally, this whole thing is just a great reminder that the best way to tackle a scary-looking problem is to just break it down into the simple, fundamental ideas that you already know.
So, to wrap this all up, let's just highlight a few common mistakes to avoid. First, always check your units. Forgetting to convert centimeters to meters is such an easy way to get the wrong answer. Second, don't let the phrase arbitrary path scare you. Remember, it's there to make your life easier, not harder. And finally, please never confuse the outward, fictitious centripetal force with the inward, very real centripetal force that's needed to keep something moving in a circle in the first place.
And I'll just leave you with a little question to think about. If you were back on the ground, in that stationary, inertial frame, there is no centripetal force. So from your perspective, what real, physical force was responsible for doing that 0.20 joules of work on the body? It's something to chew on. Thanks for joining me.